So the logic part, the first slide is about the basic theoretical presumptions behind this logic, which I will go through very quickly. So this is just a summary of kind of like the philosophy behind it. First, of course, is the assumption of insufficient knowledge and resource. This is behind my working definition of AI, which is the foundation of everything. So if we accept that, then if we want to build a reasoning system, what's the implication? One implication pretty clear is there's no absolute truth, as the name of the system suggests. Another thing is there's no algorithm, a task-specific algorithm or function or computation, whatever you call it, for the task. Okay, this is important because in AI, I think previously there are two major paradigms. One paradigm is inherited from computer science, which is kind of centered around the concept of computation as defined by Turing machine or algorithm. So whenever you want to solve a problem, you design an algorithm for that problem. As far as you can do that, the problem is solved theoretically. Okay? Or you can see it as a function which map input to the output. No matter which word you use, that's basically the same thing. But as soon as you accept insufficient knowledge and resource, you'll see this paradigm cannot be used anymore because either you don't know the algorithm or you don't have the resource to run it. For example, exhaustive search, right? If you take that as algorithm, it can be used to solve almost everything, but you don't have the resource to run it. So it doesn't count. Then the second relatively new paradigm is the machine learning paradigm, which of course does not depend on an existing algorithm, but is still revised based on that. Here, the idea is I don't know the algorithm, but I have the data. So the data give me concrete instance of the input and output which can be generalized into algorithm or usually called a function, okay? Which will map other input and output into it. So this one is different from the traditional computation paradigm, but still it's kind of like take the computation still as the goal to approximate to approach using training data. But if you really accept insufficient knowledge and resource assumption, you'll see that the machine learning paradigm cannot be accepted because either you don't have enough training data or good training data for the function, or you don't have the time required for training. Especially you'll see here we demand real-time response, okay, which almost all machine learning algorithm, even though it's running, when it really solve a problem, it doesn't take very long. But the training time typically is very, very long. Okay, if we don't give the system such a training time, you cannot use this paradigm anymore. So what you can do, that's the second part of my working definition of intelligence, that is adaptation. So which basically means that you just use whatever you have. Okay, all the knowledge you have, all the resources you have available to find the best answer, which is best with respect to available knowledge and resource. Okay, so that to me is what intelligence really means. Then reasoning, if you see reasoning from this perspective, and this will be very different from the traditional view of reasoning in the AI domain. Traditionally, reasoning is taken to be kind of like from truth to truth. They use theorem proving as the typical use case. Okay, but according to this assumption, we are more talking about reasoning not in the math context, more like in everyday context, where knowledge is nothing but your experience summarized. It's not a true description about the world. You summarize it into concepts and conceptual relations in your mind. Then use this to derive new knowledge to get what? Again, not to get truth, but to get equivalent experience. Okay? You're extending your past experience to a new scenario where you have never run into before by seeing this one as kind of like, yeah, this is similar to what I have seen. So my previous experience can be somehow transformed into this new scenario to guide our action. Still, there is no guarantee for you to be successful because the future and the past in foundation, they're fundamentally different. And you know that, but you cannot do anything better than to depend on your experience. So this is the philosophical part. I have repeated many times. But today only that slide. Okay, now let's go into something more concrete. So what we use in NARS is called the non-axiomatic logic, which consists of several layers. The first layer is the representation language, which is called NARS. As I said before, according to the previous philosophical assumption, what this language does is to express concepts and conceptual relations, and also to provide a common format, not only for the system's knowledge and belief, but also it should cover perception, action, and everything else. So this should be a general purpose knowledge representation language, which covers all types of knowledge. Then semantics, that is how to interpret the concepts. This is here the key difference between this approach and the traditional symbolic AI is do not think concepts as labels of outside objects. Instead, see concepts as a summary of experience. So what's the difference? The difference is concepts in this under this interpretation is subjective. That's what you see the world, not what the world is. So the inference rules, again, to be consistent with this philosophy, what is a valid inference rule? Traditionally, inference rule is valid as far as it's truth preserving, right? We know that. From true premise to derive true conclusion. In NARS, you can still say that, but since we have already changed the meaning of truth in a sense, it's better to see this as a justifiable pattern of derivation in the sense that it can, in such a way, to transform experience into equivalent experience of a different format, something like that. Okay. Again, you can still call it truth preserving, but it's with respect to the past. It's kind of like for your past experience, there are several different ways to talk about it, and then between them you can convert one to another. It's not preserving in a sense that it will guarantee that your prediction about the future will always be successful. Under insufficient knowledge, you don't have that, no matter what. So that's one property studied in traditional logic. Another property desired for a logic system is completeness. In traditional sense, it's kind of like can produce all truths in that domain, intuitively speaking. Okay, clearly that's not available again in this situation. But we can still talk about completeness in a different sense. In the AGI sense, practically speaking, people always ask, after we build this now in 9 levels, there is always this question whether there are still rules which need to be included in the system, or in other words, whether we really have a complete set of rules already in the current NARS. This on one hand is hard to say because complete set, well, it's undefined, right? You cannot really say clearly what that means. To compare it with the human mind is not going to lead you too far. It will give you some idea. For example, if there is an inference pattern agreed by most of human beings, say that's a valid inference, but we cannot do it in NARS, then that's a clear situation where we have one rule missing, at least one rule missing. Or you can say, yeah, if you only talk about now level 1 to 4, you can easily say it's incomplete because there's something it cannot handle. But given the current situation, it's really hard to say. At least we can say that in our application work, we haven't found a situation where the conclusion cannot be derived from our existing rules. But that's, you see, it's not a strong argument. So here, intuitively speaking, is basically say whether you can handle all the desired type of process. And here we can only justify it from empirical point of view. So just say we haven't found anything we cannot do. But really in the future, maybe we can say, in some sense, we can set up a standard. Whether our current system already achieve it is a secondary issue. The first issue is what do you mean to say you have a complete set? Okay, this to me is still an open question. But I don't worry too much just because it haven't formed a practical issue for our current work. So now you see that this is very different or completely different from the traditional symbolic AI or logic-based AI, just because it's logic in a very different sense. Okay? But it's still logic in the broad sense. When we talk about logic in our everyday life, we are talking about patterns, which are kind of like universally accepted by human beings when they're doing reason. So technically, the first thing that distinguish the logic used in NARS from everything else, especially the one you're familiar with from your mathematical logic class, is that everyone else almost is using some form of predicate logic. NARS, on the other hand, is using a term logic. Okay, and this you may already see in many of my publications, but I'm not sure whether you fully understand what is the difference between these two categories. Okay. Roughly speaking, there are two major differences. One difference is in representation. In predicate logic, the basic form of a proposition is a predicate name followed by a list of arguments. Okay, it's kind of like a P, A, B, C. Which means among A, B, C, there is a relation P. And then that's a basic proposition. Then you use conjunction, disjunction, negation, implication, equivalence, and so on to build a more complicated one and use quantifiers for all, and there exist to handle variable and so on, as you learn in your mathematical logic class. Term logic, on the other hand, actually belong to the more older tradition from Aristotle's work. Okay, predicate logic have several hundreds of years history behind it. Term logic have thousands of years history behind it. In representation term logic, every sentence, there is a subject term, there is a predicate term. Always like that. Okay, they're related together by a copula. So that's a clear difference between this category and this category. And another difference is in inference rules, not in the individual inference rules, but in the overall pattern an inference rule follows. Term logic typically use syllogistic logic rules. That is from a relation from A and B, B and C, then you can derive a relationship between A and C. Okay, with a common term in between. Today, if you take a book called formal logic or traditional logic, you'll still see a description of that kind of thing. But it's not covered in mathematical logic anymore. Mathematical logic, on the other hand, inference start from truth table, right? You all learn the truth table for conjunction, disjunction, negation, and so on, implication. So we can derive the truth of a compound proposition from the one of a simple propositions. Okay, it looks like just a difference in format, but the difference actually is much deeper than that. Okay. The current dominant opinion is to see term logic as a special case of propositional logic. That's why in today's logic class, they typically only talk about term logic when they talk about history. Okay, they think this is not as powerful as predicate logic. But why NARS use the old one? Well, that's basically what I want to show or to explain in today's presentation. So you'll see categorical proposition is a subject and copuler and predicate. And copuler, the very basic copuler or the most fundamental copuler is what we call inheritance in NARS, or in traditional AI it's called SR. Okay, that's the conceptual relation which build taxonomic structures or structures of generalization among concepts. And this one clearly is transitive. So if A is a type of B, B is a type of C, then A is a type of C. That's clearly the case. Okay. And this transitivity actually provide the very basic form of reasoning in this type of logic, that is deduction. As I said, okay. If S is a type of M is the type of P, then S is a type of P. This two is the premise, this one is the conclusion, okay, in the typical binary form. And there is no controversy here, everyone agree with that. And this can be right formally in two different patterns in most of the textbook, okay. Premise, conclusion, premise, conclusion. So the difference is just in form. And Aristotle's logic, of course, is more complicated than this. He actually distinguished 4 different types of relationship by further separate the affirmative and negative statement. That is, figure A is all as M or all as a P. E is a negation, that is all as are not P. Okay. I and O is the particular type. So some as are P and some as are not P. So by talking about the combination of positive, negative, universal, and particular, Aristotle actually distinguished 4 different relationships. You can say this A is the fundamental form, the other 3 are variations of it. But anyway, his work is completely based on this distinction, and it's all about deduction. But of course, it's just more than just simple transitivity of this A figure. And Aristotle also mentioned the concept of induction. That's actually the concept that was introduced in his writing. He mentioned this as the argument from the particular to the universal, because this is a very natural question, because what you observed, okay, always the particular. Okay, so that there is a question that if you do reasoning about the universal and where they come from, Aristotle say, oh, okay, there is an induction process, but he didn't really fully mention it or explain it in his logic. Actually, it's not part of his logic, okay? But he mentioned this possibility. Then there are a whole bunch of other works after Aristotle. The most relevant one to us is the C.S. Peirce's work. He is the one that started again from this deduction pattern. He make the observation that it can be changed into two other patterns. And these two other patterns, induction, the name was already there. Abduction was the term he picked for the third type. You'll see that it's a very elegant relationship. Induction and abduction are nothing but what he called reverse deduction, or sometimes called backward deduction. You'll see if you compare this triangle, these two are obtained from this one by exchange the conclusion with one of the two premises. Okay, you see this is from this one to and this one to this one. This triangle is from this one to this one. So it's kind of like you switch this and this in terms of who is the input, who is the output. You get abduction. The other way, you get induction. Okay, so mathematically or formally, very simple and elegant, and there is actually only this sort of possibility in this triangle. But the trouble is, of course, these two are not truth preserving. Okay, you can easily find tons of examples. Actually, that's a question I was asked by Cisco people yesterday. Okay, and they find some examples. Say, yeah, if you use this pattern, clearly the answer can be ridiculous. Of course, we all know that, right? That is why induction and abduction are difficult, just because it does not guarantee the truth, even if the premise are true. Conclusion are very often wrong. Okay. But Peirce, I think his second contribution, the first contribution to me is find this relationship. Okay. The second premise is he argued, even though these two are not truth preserving in the traditional sense, they nevertheless play a very important role in thinking or cognition. That is, abduction is typically for explanation. When you explain something, okay, and he has examples in his writing about that. Induction, on the other hand, is for generalization. If you generalize observation into another one, okay, what you do is induction. And both of them, if you think about the examples we run into in our daily life, we know explanation and generalization in general, they're not truth preserving in the traditional sense. Okay. Deduction, on the other hand, is, so deduction is the only thing that allowed when you do a mathematical proof. It guarantees the truth. If your premise are true, the conclusion will be true. Okay. And also in Peirce's writing, he said deduction is for demonstration. Okay. Abduction is for explanation. Induction is for generalization. But he still does not fully explain how to justify it. It's just because we know there are good explanation, there are bad explanation, there are good generalization, there are bad generalization. Okay, he didn't give a good example or a good way to distinguish them. But anyway, this distinction get accepted. But very interestingly, you'll see if you read today's textbook about induction and abduction, you will see that they still accept Peirce's distinction or definition, but you don't see this triangle anymore. Why? Because since predicate logic take over as the dominant paradigm, okay, they describe everything in predicate logic, which you don't have this subject predicate copular relationship anymore. Okay, So they still say, yeah, explanation is abduction, generalization is induction, but they try to define it or to formalize it using first order predicate calculus. For example, a typical situation is to say that if you see PA and PB, where P is the predicate, A and B a constant argument, then generalization means that you're going to generalize it into for every x if I should put it the other way around. If you see PA and QA, where P and Q are two predicate, okay, then you generalize it to for every x, Px implies Qx. That's the current representation of generalization. Explanation is if you already know for all x, Px implies Qx. If you see Qx, then you can use Px as explanation. Deduction, on the other hand, is if you already know for every x, Px implies Qx, and also you know Pa, you can derive Qa. Okay. You see that you still have this kind of relationship that is the abduction and deduction, and induction can be obtained from deduction by switch premise and conclusion. You don't have this kind of symmetry anymore. Okay, and that is actually one reason you cannot really move or translate NARS into first order predicate calculus. Okay, that's one reason. So now you'll see, well, actually, by the way, an interesting story. Even though this is now my way to present, the heritage of NARS, I can say from Aristotle and Peirce, but it's not really the true history of NARS development. Okay, I actually start from cell theory. It's at a very later stage. I realized what I have done is much closer to Aristotle and Peirce's work than to Caesar. Okay, so I switched that, and explain NARS in that way. I think is better, but it's not really how it was developed in the first place. But anyway, now you're familiar with NARS, you'll see that the most fundamental reasoning rule, inference rule, is the same as what Peirce defined. But the difference is I turn this from a binary logic into a multi-valued logic. And I provide a truth value function to calculate the truth value of conclusions, especially for non-deductive reasoning. So I can say abduction and induction are still justifiable, but the confidence of the conclusion will be lower than the confidence of the deduction conclusions in general. Okay, so on one hand, I still keep the difference between deductive reasoning and non-deductive reasoning. On the other hand, I found a common logical foundation say that their difference actually now is a matter of degree. It's not just in traditional logic, this is truth preserving, the other two are not. Okay, and now in NARS, you all know is truth preserving to a degree. Okay, deduction gave you a stronger conclusion, abduction, induction gave you a weaker conclusion, but they're all valid, okay? And by the same justification. Why? Because again, it comes from the previous experience grounded semantics. So that's one major difference compared to Aristotle and Peirce. And also another thing later, I realized, which is also already found by some other people in a slightly different format, is we can actually extend this into its isomorphic form. You know this pattern, right? So now we actually have 3 triangles, actually more than 3. three group of three triangle in NARS. You'll see this is the first one I introduced. Okay, they're so-called fourth order because they're based on inheritance relation. So M is a type of P, S is a type of M, and so on. Here I didn't mention the truth value function, but you'll see what I mean. And later, so this is level 1, you know, this is level 5. You'll see it's basically the same thing, but I changed this copular into this copular. You know the semantics are different. This is something, is a type of something else. This one is more like if then. This is implication, okay? Where we assume this, each term itself is already a sentence. So if this is true, then this is true. If this is true, then this is true. But again, in this higher order situation, we can also build this deduction, abduction, and induction pattern using the same truth value function, justified exactly in parallel as the first order situation. So we kind of like get this for free, okay? Just because the semantics of this implication and the semantics of inheritance can be built in parallel, even though they're not the same, right? It's kind of like this between individual or simple concepts. This, on the other hand, is between sentence. And then this one is more talking about the truth value of the two sentences. This is more talking about the meaning of two concepts, okay? But we also have deduction, induction, abduction in this format. And finally, there is a special case of the second type, which is called conditional, where if you take one of this letter as a summary of all of your current knowledge. So because of that, you can implicitly represent it. Okay, so that's the background knowledge behind the truth value. Okay? So if that's the case, then you can actually further simplify this pattern into this pattern, which is closely related to what I just said, which is the nowadays interpretation of these three types. Okay, so deduction is if S implies P, you know S is true, then you derive P is true. Abduction is kind of like the other way around. If P implies S, if S is true, you take P as the explanation. Okay, you say that's why S is true because you know that P is true. You can use that to explain. And finally, this induction is generalization. You see P and S, you generalize it to say, oh, they're not accidentally true at the same time just because one of them implies the other. Okay, that's literally what we call temporal induction in NARS. Okay, that's another form. Okay, just of course we have additional information not show up in this pattern. We're not going to allow arbitrary P and arbitrary S to derive this kind of thing, like in, in propositional logic, they do that, and then they cause so-called implication paradox, okay, all kind of trouble. We don't have that, but still there's some similarity between what we do and what they do in the traditional logic. So you'll see that this kind of thing is very, very natural in this framework. It's almost for free. You get a lot of stuff. Well, another group is what we call backward inference. It's still the same pattern. Again, a different interpretation. In this case, we will start with, we still take the green thing as the relationship, which is part of the system's knowledge, which we call a belief. But now this red thing, it's not a belief anymore. It's a question we want to answer. Okay, so we can use this pattern to do backward inference, meaning that we can derive a new question. That's this pink thing. Using these rules, under the condition, you see a conclusion for the derived question and the belief combined together will provide answer to the original question. Okay, so you know this, you want to know whether this is true, and you ask yourself whether this is true. Because if this is true, then this one will derive this one. Okay, so here I put the name in parentheses because, well, accurately speaking, it's not deduction, abduction, and induction anymore, but it will share the same formal pattern. You'll see that the triangle looks the same as before. Okay, so they cover different types of backward reasoning, also for foray. Okay, it just kind of like, why? It just because in NARS, again, in this kind of pattern is, if you have two edges of this triangle, you can always derive the third edge. And in any direction, it corresponds to different type of reasoning. So this is, in my book, I talk about the reversibility of the inference rule. Okay, but the way you reverse it, of course, they become a different type. But it still shares the same formal pattern, which is a very elegant thing of this type of logic, which you don't have in predicated logic anymore. Okay. So now you have seen this many times, right? So we can represent a simple case of the system's memory as a conceptual network, where the black links are the beliefs, and the red links are the task, say, which can be a new piece of knowledge. It can be a question you want to answer by find the truth value or find a term to play the role of a variable, something like that. Okay. And then actually this is a new example I used yesterday for Cisco people to show them, if we have that knowledge representation, then what, and the inference rules I introduced before, what NARS can produce. This is a very simple one, but I think already show the power of the system because it can combine naturally multiple type of inference in the same framework. Okay, so you'll see in this example, this one and this one, this one, and this one, they're the input with the same default truth value. Okay, and then from this tool by induction, you get this conclusion. Okay, it's kind of like Gao is the type of bird and can swim. Then you generalize it to all birds swim, which of course is not true, but is supported by this evidence. Similarly, this is induction and this is abduction. If you know robin have feather and birds in general have feather, then just because of that you can guess robin is the type of bird if you don't know anything else. But the confidence cannot be very high, okay, because it's abduction. And then you can use this and this to do a deduction, and so that you guess because of this and this. You think a robin maybe can swim. We know it's not true, and also in this system, the confidence is low. But that is the best guess the system can have, given this knowledge. Okay, you think it's ridiculous because you know more, right? If you don't know that much, if that's the only thing you know, then you should actually believe it to this degree. So, so this is an example. Another example is the one that I used in my previous talk when we talk about learning in NARS and compare it with machine learning. I think I will use it again here in this presentation. You'll see, and naturally that's also what I said, inheritance relation is typically correspond to the relationship among concepts in a concept hierarchy of generalization, right? We say Tweety is the name of a concrete robin, and robin is a type of bird, and bird is a type of animal. They're all related by inheritance relation with the default truth value. If this is what I gave to a system, then the system can do deduction, okay, can get this conclusion, and they are less confident according to the truth value function. And they can even go further to kind of like, you'll see this deduction in this case is basically use transitivity to merge a path into a single edge using the terminology of graph theory, right? When doing that, the confidence will become lower and lower because when everything can be wrong, right? If you combine many of them into one, it's more likely to be wrong compared to what you use. So that's an intuitively acceptable situation. Even though the truth value function is a different story, we are not going to go into detail. So you'll see I make a sinker and sinker just to indicate it's less and less reliable. So this is trivial. This is kind of like everyone can do. But now let's see, if I begin from this result, I begin to do induction. I observe Twitty is yellow. Okay. Then I can follow this hierarchy and using the inductive inference rule to generalize it to several different levels. Okay. And of course, when you generalize it further, it will become even weaker. So this also we can talk about, multiple generalization and its relationship with what they call inductive bias or what they call overfitting and so on. Okay. So we can talk about that later or in the future, but not today. Today there are too many things. I just show you that this generalization is completely based on logic. But on the other hand, you will clearly see the intuitive relationship with the generalization in machine learning algorithms. And the interesting part is, okay, after that, if I already reached this part, now I begin to revise my conclusion, what will happen. You see that after this, you derive this. Now I have some direct input, which tell me that this is wrong, okay? Well, let's just use this example. I would just say for some reason, I strongly believe Twitty is not animal. Here, the frequency is zero, means all the evidence are negative. Now you'll see clearly the first step is I'm going to use this one to revise this conclusion, okay? Not to completely replace it. It's kind of like a compromise. That's what the revision rule does in NARS, right? It's a compromise. It compares positive and negative evidence. So you'll see the conclusion is more negative than positive, okay? But the positive evidence is still there. So you'll say, oh, if you tell me that, I think you're right, okay? Probably this is not true. But I'm not going to completely rule out the previous evidence in this example. So this also is pretty straightforward. But now the interesting part is you'll have a process which is quite similar to backpropagation. That is, in this example, we know this is derived from this one, or from this one, okay? If the conclusion get modified, one of the premise at least should be modified. Otherwise, the system will not be consistent within itself. Actually, in NARS, both of them will get modified. Okay. Again, there's no new rule. Okay, everything I'm talking about here are just deduction, abduction, induction plus revision. Okay. So you'll see that from this one and this one, the old stuff is still there. Okay, I didn't copy it into this side, just to make it relatively simpler. So from this one and this one, you get a new convolution between these two, which is more negative than positive. And then that one will be merged with this one to get this result. Here you see I skipped several steps and just show you the final result. Otherwise, it's too complicated. But you can actually verify this using our code. Okay, you will see the intermediate steps. So this tool will have the same truth value. So you'll see here is still more positive, okay, between the two, but it will get some negative evidence. The same thing happened here and here. Okay, if you see the final result, you will see it's kind of like this negative evidence will have some impact to all the original relationship, but to different level. Okay, and this one will actually share the same truth value here. This one will have this truth value. Okay, you can see that it's not equally punished. The one toward the beginning and the end are punished more than the one in the middle. If you add more than 3 layers, you will also see that effect. Okay, that's an interesting thing. We can further discuss, but it actually is consistent with psychological data, which say that if you're processing a sequence of things, and what you remember best are the one that toward the beginning and the end, or you process them more than the one in the middle. Okay. But of course, the numbers themselves depend on the concrete design of NARS. So I want to use this example to show you the intuitive relationship between NARS and the machine learning, and also show you why we say in NARS reasoning and learning is actually carried out as the same process. Okay, you'll see again, there's nothing new but the 4 inference rules. But if you concentrate on the final effect overall, what you see is a learning process which actually similar in a sense to the current machine learning. And actually, induction abduction itself is similar to urban learning, okay, to a certain degree. And this is similar to backpropagation to a certain degree. So this is typical syllogistic rule, but in NARS we also have non-syllogistic rule, or in traditional sense is non-syllogistic. Because syllogistic in the classical sense means, again, that triangle form, okay? You have 2 premises with a shared term, then you build a conclusion between the other 2. That's a typical syllogistic. There are other things, but more or less in the format, I call it pan-syllogistic format, means somehow similar to syllogistic, where I use this, it's called compositional rule in NARS as an example, okay? You'll see that, again, the dark green are the given premise, okay? You have inheritance relation from T to P and Q. If you do syllogistic reasoning, you'll see the pattern is induction. And what you get is the relationship from P to Q and from Q to P symmetrically. Okay? We do have that, but we have additional results. If you feed this into NARS, you will see it will also create a new term, not just build a new relationship. It will create new nodes to summarize those relationships. Okay. Here we create what we call extensional intersection, and this is what we call intentional intersection, or you can call it extensional union. Okay. So the final result is the system is going to also create these 2 nodes and build relationship from T to them as a summary of the original one. So you'll see on one hand, it's not syllogistic in the traditional sense, but it's still pretty similar, especially in the selection of premise. That is, it must be 2 premises with a shared term. Otherwise, these 2 are not semantically related to each other, and they're not going to be used together to derive a conclusion. Okay, and what I draw here in blue, I kind of like gave you the literal meaning of those new compounds. Okay. This one, P and Q, is kind of like something have an inheritance to P and the inheritance to Q by definition. Okay, that's the literal meaning, which have kind of like this. Everything here are both this and this together. Okay, is what this intersection means intuitively. Okay. Union, on the other hand, is a more general one which cover both P and Q. So if it's in P, then it will be in P or Q. If it's in Q, it will also be in P or Q. So those things are kind of, you can say it's an analytical truth. Okay. But if you say, oh, NARS does not allow any truth, well, we have a way to handle this, right? So you don't directly see this relation in the memory. But this will be turned into inference rules, actually, to generate convolution. So in the future, if you have T is a type of P, then the system will derive T is also a type of P or Q. Okay, that's embedded in the inference rules. Anyway, most of the inference rules, almost all of them, are pan-syllogistic in the sense that it will take two premises with a shared term. The exceptions, of course, are the one that depend on temporal or spatial relationship between two things. So those does not have to share a common term. Then what? Then a major extension of the previous picture is to extend it into procedural inference. So statement can be an event if there is a time attached to its truth value. It can be an operation if the system can execute this, can make it true. It can be a goal for the system to pursue. And also truth value can be changed into desired value to indicate how strongly you like this goal, especially when you have multiple goals which conflict with each other. Okay, I'm not going to talk about the detail of this. I just show you that all of those things eventually absorb all together into this conceptual network, which we call concept-centered representation. And you'll see that all the reasonings eventually fell into this pan-syllogistic format. Okay, so we just, a concept is nothing but a node which relate to other nodes and their relationship among them. And you'll see that all the reasonings build new links or build new nodes in this network. And also, of course, because of the resource restriction, we also keep deleting things from it so that the system's resource can support. And a small number of terms and relations are innate, and most of them are learned by the system. So that's kind of like the control structure. Now let me summarize the result. You'll see that even in today's AGI field, even though it's already a small field, to do logic-based system is even smaller. Okay, actually, we are probably the only one can be called a logic-based AGI. Okay, many other systems use logic, but use logic to build part of the system, and they also use something else. NARS, logic is everything, but of course you can describe it from a different perspective. You don't have to call it logic; you can call it a network. And describe it in that way, right? But at least there is a possibility to completely explain the things using logical relationship. What's the advantage? You'll see that we find a way to combine or to put the logic on the foundation of insufficient knowledge resource. Okay. And also provide unification in representation and processing, which fit the previous representation picture and will handle all types of knowledge, like what they call semantic. For example, in cognitive architecture, which we analyzed several of them in the past, okay, they typically have a separate memory for semantic knowledge, procedural knowledge, episodic knowledge, and so on. Why in NARS we only have one memory? It's just because we have a unified representation. And also we can treat reasoning, learning, categorization, and so on, all in the same pattern because of this logic. And also we can actually see everything as concept substitution. They go back to my first slide. You see reasoning is what? Reasoning is a way to turn your previous knowledge equivalently into a new format so that it can fit into new situation you never run into before, for which you don't have direct experience. Okay, and if you have direct experience, then what do you need? It's just a memory and a recall mechanism. You need reasoning because this is new. You never seen it before, but you have seen something related to it, so you convert those into a format which can be, again, like you know relation between A and B, and you know relation between B and C. From that, you derive an equivalent relationship between A and C, which you can directly use to solve the problem you're facing. That's what reasoning is about. It's not from truth to truth. So that's a very different opinion about logic and about the reasoning process. And you'll see I also mentioned reasoning can also be extended to handle something traditionally does not belong to the logic territory. But that's not my invention, right? If you know Prolog, you know that's logic programming. They have already done that. I will just combine that, also extend it from binary to multivalue. And also we integrate sensory motor into the picture. And compared to machine learning and deep learning, even though they can do a lot of things, we still have the advantage of we use justifiable rules and explainable results because we do everything at the concept level. Okay, and there's a logic which is different from the traditional rule-based system. The difference is in logic, every rule has a justification independent to the concrete application. Okay, you know that deduction rule is always justifiable no matter what is the concept involved. And why people do not want a traditional logic-based AGI? They just whenever they see one, they say, "Oh, that's a symbolic AI. Symbolic AI failed already." Yeah, symbolic AI failed already. Not because they use logic, because they use the wrong logic, according to my opinion. Especially because they use the wrong semantics. They try to talk about the truth in the world. There is no such a thing. Okay? So I think by change that to talk about the experience of the system, giving up the hope to get absolute truth. And also switch from traditional logic framework back into Aristotle's term logic, of course, properly extended. I think we can still get the good thing of symbolic logic, but avoid the trouble, at least all the troubles we have heard about of symbolic logic by using a new logic, okay, rather than move to connectionist approach, which I think there are some good things, but there are a lot of trouble also in that. And at the end, this is not just an attempt to build an AGI. It's also a model which can be used to explain human cognition in many aspects. The major reference, of course, is that book now.